we can now talk about phenols. Phenols are organic compounds where the OH group is attached to a benzene ring carbon. As we said earlier, in phenol, the COC bond angle is 109 degree. Now, when you examine the molecule of phenol, you can find that the oxygen has two non-bonded pair of electrons. These two non-bonded pair of electrons enter the ring by resonance, resulting in the following resonating structures. When we examine the resonating structures, we can find that the negative charge resides on carbon atom 2, carbon atom 4, carbon atom 6. The electron density of the benzene ring has increased. So, hereafter phenol will show electrophilic substitution reaction faster. The negative charge is found to be going to the position 2, 4, 6. Therefore, further electrophilic substitution reactions will take place at 2, 4, 6. So, it is an ortho-para directing group. Another very important feature of the resonance in phenol is that among the 4 resonating structures, we can find that in 3 resonating structures, the oxygen bears a positive charge. We know oxygen is electronegative in nature. Once it becomes positive, it develops an instability. Therefore, oxygen has now a tendency to become stable. The easiest way for it to become stable is to get the bond pair electron of the OH bond in such a manner that the bond pair is taken up by the oxygen and the H plus is released. Okay. Once it releases H plus, whenever some compound releases H plus, we say it is acidic in nature. Not only that, in the case of phenol, once a phenoxide anion is formed, when you compare with that of alcohol, there the alcohol, the neighboring group was an alkyl group. Alkyl group was an electron releasing plus I group, and therefore the anion, alkoxide anion, there was unstable. Here, once a phenoxide anion is formed, the newly acquired pair of electrons enters the ring and it gets stabilized by resonance. So, in the phenol, the phenoxide anion is stabilized. Therefore, it shows acidic character very fast. So, when we take alcohol, treat it with sodium hydroxide, there is no reaction. But when we take phenol and sodium hydroxide, it dissolves, indicating that it is acidic in nature. Okay, and we get what? Sodium phenoxide. So, we can differentiate between alcohol and phenol, both are OH bearing compounds, but in alcohol it is not acidic in nature, and therefore, when you treat with NaOH, there is no change. Whereas phenol reacts with NaOH and it is soluble in NaOH because it is acidic in nature, forming phenoxide anion. So, we can differentiate alcohols and phenols also based on this. So, the resonance causes 3 important things or changes in phenol. 1, electron density increases, therefore, electrophilic substitution reaction takes place very fast. It is almost considered to be numerically almost 7,000 times faster than in benzene. Second, the reaction takes place or the electrophile goes only to position 2, 4, 6. So, it is an ortho-para directing group. The third most important feature is that the phenol is acidic in nature because of the resonance. So, these are 3 important consequences of resonance on phenol. So, when we examine the properties of phenol, we can easily classify them as follows. Phenol reacts with sodium to form sodium phenoxide. Phenol reacts with sodium hydroxide to form sodium phenoxide. Phenol, when treated with sodium bicarbonate is a weak base, phenol also is a weak acid. So, when treated with sodium bicarbonate, there is no change. So, it can be used to differentiate between acid, because acid reacts with sodium bicarbonate, phenol does not react with sodium bicarbonate. Okay. When blue litmus is dipped in phenol solution, it becomes what? Red. So, that again proves that it is acidic in nature. Next, acidity of phenol is due to this stabilization of the phenoxide anion due to resonance. There are substituted phenols. Substituted phenols, there are 2 types of substituents we know. One is the activating group, that is electron donating by resonance or inductive effect, or electron withdrawing groups, the other deactivating groups. So, there are 2 categories of groups that can be on phenol. CS3 is an activating group. It releases electrons into the benzene ring. Therefore, phenol's oxygen's electron cannot enter the ring easily. Therefore, it retards. All activating groups retards the entry of oxygen electron into the benzene ring, and therefore, formation of phenoxide ion is retarded. Therefore, all activating groups decrease acidity. Methyl phenols are less acidic than phenols. Okay, methyl phenols are also called as cresols. Now, let us take the case of a deactivating group. A deactivating group like nitro group increases acidity. Why? Because the NO2 group withdraws electrons to the benzene ring due to its deactivating character. This will facilitate oxygen's electrons entering the ring faster. As a result of it, it becomes a phenoxide anion faster, and therefore release of H plus is therefore faster. So, we say it is a stronger acid. So, activating groups decrease acidity, deactivating groups increases acidity. Now, let us compare the three other substituted nitrophenols: orthonitrophenol, metanitrophenol, paranitrophenol. The orthonitrophenol should have been more acidic than paranitrophenol or metanitrophenol, because it is very close to the OH group, and its electron withdrawing tendency will be strongly felt by the neighboring OH. But when we compare the acidities of the orthonitro, metanitro and paranitrophenols, it is found that the paranitrophenol is slightly more acidic than the orthonitrophenol. The reason for this is in the ortho position, an intramolecular hydrogen bond is generated between the OH hydrogen and the NO2's oxygen. As a result of what? A 6-membered intramolecular hydrogen bonded cyclic system is formed, and therefore, the removal of H plus is a bit retarded. Therefore, paranitrophenol is slightly more acidic than the orthonitrophenol, followed by the metanitrophenol. So, this is a question that is asked. So, always remember, paranitrophenol is slightly more acidic than the orthonitrophenol. Similarly, this feature characteristic of the intramolecular hydrogen bond is used to separate a mixture of orthonitrophenol and paranitrophenol. Orthonitrophenol, due to the intramolecular hydrogen bonding, what happens? It has a lower boiling point compared to the paranitrophenol. So, we can use steam distillation to separate a mixture of orthonitrophenol and paranitrophenol. Which has a higher boiling point? Paranitrophenol has a higher boiling point than orthonitrophenol, because there is intramolecular hydrogen bond in the case of the orthonitrophenol. Okay. This also much can remember. Now, let us get into the other electrophilic substitution reaction generally shown by phenols. Phenol can undergo nitration. Here again I want to classify them as a mild nitrating agent and a strong nitrating agent. Dilute nitric acid, mild nitrating agent. So, when you use dilute nitric acid, you get either orthonitrophenol or paranitrophenol. But when we use concentrated nitric acid sulfuric acid mixture, is a stronger reagent. There in that case you get what? 2,4,6 trinitrophenol. This is also called as what? Picric acid. So, with mild you get only ortho and para, with stronger you get what? 2,4,6 trinitrophenols. Similarly, we can examine the case of bromination. Bromination also can be carried out with mild brominating agent or a strong brominating agent. Mild is bromine CS2, a non-polar, non-protic solvent like CS2. Bromination is mild, therefore, you get either ortho-bromo or para-bromophenols only. Whereas bromine in water, in a protic solvent like water or a polar solvent like water, you get what? 2,4,6 tribromophenol. So, this also is different. In all other cases, you do not have mild or strong. For example, in the case of chlorination, you get only ortho and para. Okay. In the case of alkylation, you get only ortho and para. In acylation, you get only ortho and para. In sulfonation, you get ortho and para. In sulfonation, the main product is para, because the orthosulfonic group and the acidic OH group is, there will be a strain, there will be a repulsion. So, the more product that is obtained in larger amount is what? The para sulfonic acid phenol. Okay. This is an interesting thing. So, only in the case of what? Nitration and bromination you got mild and strong. In all the cases, you do not have a mild or strong. That again you remember. Phenol reacts with carbon dioxide in the presence of a base like NaOH. resulting in the formation of orthohydroxybenzoic acid. This reaction is referred to as the Kolb's reaction. So, in Kolb's reaction, what happens? The C double bond O carbon dioxide, the carbon is attacked by the negative charge on the ortho position, resulting in the formation of an anion, carboxylate anion, which due to the presence of sodium hydroxide forms a sodium salt. Subsequently, when HCl is added, it releases the orthohydroxybenzoic acid. This compound is called as salicylic acid. Salicylic acid is a very important starting material to form different other products. So, that is the importance of this reaction. So, salicylic acid has an OH group and a C double bond OH group. Therefore, salicylic acid can further be treated with an alcohol or with an acid. We know that alcohol will not react with the OH group, it will react with the acid to form an ester. So, you get methyl salicylate. When you treat with acid, acids will not react with COH. So, COH will be intact, it will react with the OH, resulting in the formation of what? A compound called acetyl salicylic acid. This acetyl salicylic acid is what? Aspirin, used as a drug for relieving body temperature and headaches. Similarly, methyl salicylate is oil of wintergreen or the oil found in eucalyptus oil. So, these are two important commercial things that can be produced from the salicylic acid resulting from the Kolb's reaction. Another interesting reaction is the Reamer-Tiemann reaction. Reamer-Tiemann reaction makes use of phenol with chloroform in the presence of NaOH. When phenol is treated with chloroform is CHCl3. Once you say CHCl3, the product is salicylic salicylaldehyde. It is CHO. So, this reaction is called as what? Reamer-Tiemann reaction. So, phenol CHCl3 in the presence of base results in the formation of orthohydroxybenzaldehyde. This is called as what? Salicylaldehyde. So, you can easily remember Kolb's reaction and Reamer-Tiemann reaction. Kolb's Co means COO means carbon dioxide, COO means the functional product is COH. It is salicylic acid. Reamer-Tiemann reaction, please do not use the word chloroform, use it as CHCl3. Once you say CHCl3 3-4 times, immediately the functional group that will come into your mind is CHCl3 CHO, CHCl3 CHO. So, the product will be salicylaldehyde. So, these are two important interesting reactions in the presence of a base like NaOH. You have always seen that whenever a tree is cut or a branch is cut, you find the trunk that is broken away has a pale pink color, pale cream color, slightly flesh colored. Now, after a period of time, you find that it has become darkened, it is almost brown in color. Why is this change? For that, you must always remember that phenol is one of the most important constituent part of the tree trunk. So, whenever a trunk is cut, it has got fresh phenol in the molecule. But phenol, when kept open, it undergoes oxidation, resulting in the formation of benzoquinone, and that is why you get the brown color. So, this benzoquinone formation is the interesting part of any phenol molecule. So, when a phenol bottle is freshly kept in the laboratory, it is colorless in solution, color. But when you kept for 5 or 6 months, if it is kept open, it becomes brown in color. Why? Because benzoquinone is formed. Okay. Phenol can be converted to benzoquinone even by adding slight mild oxidizing agent like CrO3. So, when phenol treated with CrO3, it results in the formation of benzoquinone. So, this is also an interesting thing. Another interesting reaction of phenol is when phenol is treated with zinc dust, it results in the formation of benzene. So, this again is another important reaction of phenols. So, these are the most important things that you must know on phenol. Phenol is a very important compound used as an intermediate to prepare large number of organic compounds, synthesize large number of organic compounds. But always remember, phenol is highly carcinogenic, handling of phenol should be very careful, and almost all dyes have phenol, and therefore, we say that all synthetic dyes are bad because phenolic compounds can form cancer, can induce cancer. So, these colored compounds, most of the colored compounds can have what? Phenol in the molecule. In laboratories, phenol is tested by using neutral ferric chloride. When neutral ferric chloride is added to a phenol solution, we get a violet color. This is a characteristic test for phenols. We get a ferric phenoxide complex which is violet in color. It's a very characteristic test. Similarly, naphthol, that is naphthalene with an OH, is naphthol. It gives a green color with neutral ferric chloride. Gallic acid is 3,4,5 trihydroxybenzoic acid. That again with neutral ferric chloride gives a dark blue color. Pyrogalol is 1,2,3 trihydroxybenzene. When treated with neutral ferric chloride, we get a wine red color. So all phenolic compounds give this test. Salicylic acid, we all know, is hydroxybenzoic acid. When treated with neutral ferric chloride, you get a beautiful purple violet color, like that of KMnO4. Sulfosalicylic acid is salicylic acid with sulfonyl group. Here again we get a wine red color with neutral ferric chloride. Hydroquinone is 1,4 dihydroxybenzene. This again with neutral ferric chloride gives a dark brown coloration. So neutral ferric chloride can be easily used for all types of phenolic OH. It gives characteristic color, and even the colors can be used to distinguish one from the other. So ferric chloride with phenol gives a ferric phenoxide complex, which is responsible for the color.